시작해도 될까요? Okay, good afternoon. This is my lecture time. I am seungwhan. We learned about the resistance of a ship. I will explain again about major resistance component like this. Two major components of a resistance is at first frictional resistance to overcome viscosity. Second, residual resistance, largely wave making. In the case of frictional resistance depends on the wet surface area of the hull. At this point, if we use a smooth hull surface, we can make a good we can make the minimize frictional resistance, and we can make the good hull bond. Okay. Sorry. Okay. If we use the smooth hull surface, we can minimize frictional resistance, and also if we use a good hull bond, we can minimize residual resistance. In two cases. And to compare the two resistance, in most ships, the frictional resistance is 3 to 4 times as large as the residual resistance. And but in relatively high-speed ships, do you know the example of high-speed ships? Maybe the example of high-speed ships is battleship. Oh, okay. And in the case of battleship, the two resistance, frictional resistance, residual resistance, might be about equal. That have the same magnitude of resistance. And in power divisions, as you can see, there are 5 power like this. We can start from this engine, prime mover. And prime mover is connected to gear and long shapes and propeller and like that. Okay, at first, effective power is total resistance multiply total uh, total resistance multiplied to speed, like that. Each power is related to the individual efficiency, like this. More detailed efficiency is on the next slide. Okay, like this. In power estimations, in the effective horsepower and propulsive coefficient is effective power over delivered power, like that. If you calculate like this, you can acquire the result like this efficiency product. So it can be represented as 3 efficiency like this. The first is whole efficiency, NH, and it was thrust deduction over wake gain, like that. And the second, open water propeller efficiency, NO, and third, relative rotative efficiency, third, NR. Okay, this propulsive coefficient is composed of the product NH whole efficiency, NO, NR. Okay, you can calculate like this. Okay, and the next topic is engine selection procedure. Okay. How can we select the engine we want? This is very important to engineering and us. So most people comply with this procedure like this, this order. Okay, early the best at first estimate frictional horsepower and estimate wave making horsepower, and add-on power requirement increment for appendage. And also we should calculate the sum of the above mentioned powers, frictional horsepower, wave making horsepower. We should sum of the above powers, okay, will be the estimated effective horsepower (EHP), and we should also come to the delivered horsepower and then add a few percent for shape losses to get SHP and PHP. SHP and PHP will be in next slide. Okay, and add a power margin, C margin for actual service conditions at C, typically 15 to 25%. Okay, also maybe if we to this procedure, finally we select engine that we want or turbine from engine manufacturer's catalog. Okay, so and then submerged bodies like this. Okay. As you know, submerged bodies means world of deeply immersed body moving at a constant speed. There is no free surface, no wave formation, and therefore no wave making resistance. In an ideal fluid means without viscosity, the body experience no resistance. The people call this onboard paradox. It is called paradox because it is contrary to everyday experience. However, since the actual fluid has a viscosity, the object has a very small resistance. So people call this paradox. Okay, and the next topic is surface shifts. Surface experience resistance burst. So it has the same wave comparing to the submerging body like this. In addition, the presence of the free surface as wave making resistance, the wave must overcome gravity also, which will absorb energy. Okay, this similar ways to submerged bodies. And in terms of energy, what happened to the energy in maybe you can know the expression in the shaped bearing and the seals 1 to 2%, and propeller convert to torsion energy in thrust, which is nearly 70% efficient. And then propeller hole interactions. There are two interactions like this: wake gain, thrust deduction. At first, wake gain, the propeller operates within the relatively slow moving water, which enable regaining some of the energy. This means we can save the energy from wake gain. And second, thrust deduction, the propeller reduced the water pressure on the stern. More work, more energy is required to overcome this pressure-induced suction. This is in terms of energy. And then last topic is estimating horsepower. The important thing is one of the most challenging responsibility of a naval architect is selecting an engine that will drive a proposed ship at the right current speed. So in this point, the engine that we want is very important. Okay, and the horsepower. Horsepower. The definition of horsepower is a unit of measurement of power. This is a product of force and speed. Okay, this unit, 1 HP, 75 kilogram per second. And then last is engine output. As you can see, these two at first brake horsepower bhp in diesel or gasoline engines, and second shape horsepower shp. SHP is steam turbine. Okay, what you should remember is that note PHP and SHP are identical in a direct drive diesel engine. In a direct drive diesel engine, PHP and SHP have the same magnitude. Mm. Okay, in this point, my lecture is over. The professor will proceed in the remaining part. Thank you.